Hello guys, this is part 4 of circular motion. Let's see if I can finish it up, if I can wrap it up in this video. A couple of variables that I haven't talked about yet. First one is called the period. Period is a time required to complete one full cycle, okay, one revolution. That is called period in seconds. Capital T is the letter we're going to be using for period, not to be confused with tension and force, right? Separate things. And the reciprocal of the period is called frequency, which is 1 over time, 1 over period. Okay, so the unit will be 1 over seconds, or hertz, as it is called. So it takes t many seconds to complete one revolution about a center. Okay, the circle has a radius r. This is the velocity around the circle. The circumference is 2 pi r. This much distance is covered in t seconds with this linear velocity. All right, so v is 2 pi r over t. Okay. Now you have here an angle over time multiplying the radius. All right, and if you remember from previous video, we have this thing called the angular velocity, omega. Now the average angular velocity was delta theta by delta t, right? Now, when I wrote this formula, of course, I assumed that v was a constant, right? Just to make a point here. If v is a constant, omega is a constant as well. And you can take theta to be the full cycle, 2 pi. In that case, this will be equal to omega times r. All right? 2 pi over t will simply be equal to omega. But now this relation is true for any kind of acceleration situation. Okay, right now a is 0, but what if a was not 0? What if it was speeding up? We could still write this relation now. Okay, these are for instantaneous values of omega and v. Okay, pretty much a rotation about a center involves two kinds of velocities, the angular velocity and linear velocity, and this is how they are related. Okay, now imagine a record. Okay, you're on your turntable, there's a record. Okay, here's the arm and then the needle. All right, and it's spinning this way and all right? So when you play your record, in the beginning of the side A, you know, the needle is right here. But towards the end of side A, this will be the location of the needle. All right, in the beginning of the song and the end of the song, or end of the, if it's a single, it's just one song, right? At the end of the record here, right there. Now, the number of revolutions for a typical record is 33 1/3 revolutions per minute. Okay, that's omega in revolutions per minute. And one revolution corresponds to 2 pi radians. So if you wish, you can convert this to radians per second easily. You just have to multiply 33.3 revolutions per minute. Revolutions per minute. Okay, so 1 revolution is 2 pi radians, and 1 minute is 60 seconds. Okay, do the math here, and it will give you, once you get rid of the revolution and the minute here, it'll give you the answer in radians per second. Sometimes it's 45 revolutions per minute, right? Those signals from 60s, 70s. All right, the point is though, while it is rotating, at any given time, omega doesn't change, okay? Omega is a constant. No matter where you are, omega is a constant. But as the record goes on, you know, you listen to the song, this needle gets closer to the center, which means R goes down. R becomes less and less. We're talking about a point here, the point of contact of the needle to the record, right? If R goes down, so does V. But omega is a constant. Okay, this is opposed to CDs. CDs are different. In the case of a CD, we have a laser reader and some digital signature here, or digital recording, ones and zeros, okay? So V is a constant. When R changes, omega changes for a CD. If I'm not mistaken, CDs work that way. So that's the relation between V and omega, okay? For any object, actually, for a rigid body, which is under rotation, every point on that object has the same omega. But V, linear speed, linear velocity, depends on where you are, depends on how far you're away from the center. Okay, farther away, greater is V, greater velocity. All right. A similar relation is between alpha and the linear acceleration. This is A tangential, if you recall. All right, so a similar relation is between the linear and circular, rotational, or angular alpha, angular acceleration alpha. All right, that's what I wanted to talk about. The next thing in our list is what to do with dynamics. This is all good, fine. You now know how kinematics works, but how do you solve real-life problems which involve things like force and mass? Okay, so for today, I'm not going to go into rigid body rotations like this compact disc or record, but instead focus on point particles going in circles, okay? And when we do rotations, we're going to revisit rotations. I'm going to talk about the generalization of these concepts of force and mass for rotations as well, but not today. So let's go back to point particles moving in circles, all right? This is a mass. It could be a satellite, communication satellite in orbit around Earth, okay? So I'm ignoring the dimensions of the object. I'm treating it as a particle, point particle. This is the center of the circle. This is the radius, R. Now, if this object is moving along a circle, we know that there's acceleration, okay? Whether it is speeding up or slowing down, or moving with constant speed, doesn't matter. Just because it's a circle, there will be an acceleration which points to the center, okay? Centripetal acceleration. This will never be 0, all right? So you remember the form that was derived in part 2. AC will be equal to V squared divided by R, centripetal acceleration, all right? So when the object is here, now the velocity maybe points this way. It used to be this way over here. This was V, now V, which is still perpendicular to the radius, but the acceleration is to the center again. Centripetal here, again, to the center. Okay, no matter where you are, the acceleration will point to the center with this magnitude, V squared over R. So now that we know what A is, all we need to do dynamics is to go back to Newton's law, Newton's second law, which says the net force, or the vector sum of all forces acting on body, is equal to its mass times its acceleration. All right? So if there's an acceleration which points to the center, that's because there's a force in that direction. There's a force in that direction. There's a force in the same direction. Okay? This is F. The net force. If we're talking about a communication satellite, the force is the gravitational pull of the Earth on the sun. All right? If you tie a string to a ball and then start spinning it, this force will be the tension in the string. All right? If we're talking about race cars on a racetrack, then this will be a combination of friction forces between the tires and the road and also the normal force. Okay, I'm going to go through a couple of examples, but these forces will add up to give a net force right there. This is by definition net force, F net, the vector sum of all forces. That will be equal to mass times acceleration, right? So if we just find this F, I'm just writing the magnitude now. That will be equal to m times v squared over r. Okay, that's how you solve these problems. Here's a problem for you. An example. Example 1. Let's say you're driving a car on the highway, all right, and the road is straight. You're driving in the desert or something in Arizona, Nevada, all right, the road is pretty straight. You're on cruise control, constant speed. And then, for some reason, for some geological reason, you're going through a really large ditch. Okay, that looks like this, and then straight, okay? But your car is really small compared to that ditch. All right, so here's at the bottom of the ditch. This is your car, and then finally you leave it again. Okay, and while you're doing this, you're on cruise control, so V is not changing. Constantly, just to make it simple. All right. Now let's try to apply this principle here of acceleration. Okay, now you may be saying, okay, what acceleration, right? I mean, you just said constant speed, cruise control. You're not speeding up or slowing down. Yes, as long as you're going along a straight line. Now, once you're inside here, once you're here, you're no longer going along a straight line. There's a curve to it, okay? It's not a circle, but it is like a circle. Like I could just fit a large circle here. All right, this could be the circle we're talking about. It is a circular motion. Partially, it's there, which means there will be an acceleration, which points to the center of the circle, which means this way. Okay, that is the direction of the acceleration. All right, so be careful though. This acceleration over here will be this way. Here it will be that way. They have to point to the center of the circle. All right, but I'm interested in here at the deepest point of this ditch. Now, if there's acceleration, according to Newton's second law, there must be force. Right? There must be a net force. So what I need now is a free body diagram. A free body diagram. Let me draw it here. This is the vertical direction, call it Y. Horizontal direction, call it X. Okay, and now I'm gonna show my forces on this free body diagram. So there's the weight of the car, which never goes away, right? mg. And now I have to worry about the normal force as well, which is going to be up. This is the force that the road exerts on the car. Okay, it lifts it up. Now, when the car is here, I don't have any reason to think that these two are going to be different in magnitude. Let me label them. So this is weight, mg, which is weight. And this is the normal force. I'm going to use Fn to show normal force. Okay. Normal force. But now I have acceleration. A. Therefore, there must be a net force. These two cannot be equal to each other. In terms of magnitude, Fn actually has to be greater than mg. So that when I subtract mg from F, there's still some force there, which is responsible for this acceleration. Mass times v squared over some radius r, which will be measured from the center all the way to here, right? That's your radius. Okay, so your equations of motion, or equation of motion is here. Fn, normal force, minus mg is equal to m times v squared over r. Now what to do with this? Well, I can rearrange it. I can write Fn as, bring this term to the right-hand side and factor m out. It'll be positive, of course. G plus v squared over r. Okay, so the normal force at the bottom is going to be greater than the actual weight of the car. Okay, so if this was, let's say, a bus, and then you're standing on top of a bathroom scale, right? And when the bus is here, the bathroom scale would read your actual weight, right? But when you're here, when at the bottom, the bathroom scale, which shows the normal force, will show you a number which is greater than your actual weight, okay? It's called the apparent weight. Okay, similar effect when you are using elevators, right? When it starts moving up, you'll feel yourself maybe heavier than usual. Okay, well, this is not that interesting. What about a similar case? Let's say you're driving on the same road, okay, but now there's a little hill or a bump on the road that looks like this. Okay, here's your car again, and now we're at the top of that bump and back again on the road here later. But same idea. Okay, now on the top of that little mound here, you have this radius, you have this curvature. All right, so there the acceleration points downward. There's acceleration pointing downward here. A, which is v squared over r, which means there must be a net force in that direction. Okay, so here's your free body diagram. mg downward and the normal force upward, but the acceleration is downward. The net force has to be downward. Therefore, mg minus Fn is equal to mass times v squared over r. Now here's the interesting thing. If you solve this for Fn, like we did before, okay? If you solve it for Fn by bringing this term to the right and this to the left and factoring out m, you will have g minus v squared r that is multiplied, hang on, that is multiplied by m. What's happening now? Okay, just setting. All right, so let's go back here. I'm just going to put R. All right, so Fn, the normal force, is equal to mass times g minus v squared over r. Now, look at this negative sign here. Okay, you subtract this from g, which means the normal force is less than usual. The normal force here. The normal force at the top of the hill is less than the normal force when the road is straight. You're actually subtracting this term. Faster the car, faster you're driving, greater what you subtract from g, right? So there will be a point, if you go fast enough, there will be a point when Fn will be 0. So if or when Fn is 0, or maybe I said it backwards, if g times r, and you take the square root of that, if this is your velocity, okay, this critical value, then this will be 0. Then the normal force will be 0. Okay, you lose contact with the road, you start flying, all right? So this is your maximum velocity. Under normal conditions, you have to drive slower than this critical or maximum velocity, all right? So let me give you one more example. All right. What about this toy car going down a slope? And then there's a loop here. And then this toy car, which goes down, will enter the loop, start climbing up. Then here will be upside down. Then leave, okay? Now, at this instant, when it is at the top, let's see what happens there. The normal force will be pointing downward now. That's the normal force. By definition, it's the force that the track exerts on the car. Okay, it's going in a loop like that. But its weight is also downward. Let's use a different color to show weight. This is weight, okay, the one in blue. So both weight and the normal force are pointing in the same direction. If I use Newton's second law again, the weight, mg, plus normal force, this is my net force, which is equal to mass times v squared over r. V is this way, right? Now, if you solve this equation for Fn, you will get m v squared over r minus g. This looks very much like this one, except for a negative sign. But it still tells you about this critical velocity here, okay? If this condition is satisfied, then this is zero. Then the normal force becomes zero, which means your car will not be on the track anymore. You will lose contact, all right? You don't want that. This means, in order to complete the loop without becoming a projectile along the way, right? Your velocity should remain above this critical velocity. Not below, but above. It has to be greater than the critical velocity. All right? So, looks very similar, but there's a difference. Okay. All right, I'm going to stop there.